Remainders in alternating series theorem. Let the summation -1 to the power k plus 1 times ak be a convergent alternating series with terms that are non-increasing in magnitude. Let Rn equals S minus Sn be the remainder in approximating the value of the series by the sum of the first n term. Then the absolute value of the Rn is less than or equal to An plus 1. In another word, we can say the magnitude of the remainder is less than or equal to the magnitude of the first neglected term or the an plus 1 term. Examples. The natural log 2 is in the form of the alternating series as 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 and so forth, or in the form of the summation of -1 to the k plus 1 divided by k. How many terms, or looking for the n, that are required to approximate the natural log 2 with the error less than 10 to the power -6, or we can say that we're going to find n such that the absolute error, which is from the exact minus the approximate less than 10 to the -6, and the exact value, which is the natural log 2, or we use the s as the sum of this series, and the approximate. That means we're going to use the first n term, or we use the partial sum Sn notation. So then the absolute error, which is the absolute value of the s minus Sn, which is the same as the absolute value of the remainder term, must be less than 10 to the -6. And by the theorem, the absolute value of the Rn is less than or equal to the absolute value of the An plus 1 term. And the absolute value can be ignored for the An plus 1 because the An plus 1 always positive anyway. So the absolute value of the Rn, which is less than or equal to the An plus 1, must be strictly less than 10 to the -6. Therefore, the An plus 1, which is from the AK, which is 1 over k. So then AK plus 1, or the An plus 1 would be 1 over k plus 1. But we use the notation n as the number or the index of the term on how many terms that what we are looking for. So An plus 1 is 1 over n plus 1 less than 10 to the -6. We're going to solve for n. Therefore, the n plus 1 is greater than 10 to the power 6, or n is greater than 10 to the 6 minus 1, which comes out to be 999. So n has to be greater than this number. So the first number that is greater than 99999 is 1 million, or at least we need n equals 1 million, or 1 million terms to control the error, to have an error less than 10 to the -6. Second example, consider a series -1 plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial and so forth as the summation of the form -1 to the power k divided by k factorial. We're going to find an upper bound for the magnitude of the error in approximating the value of the series, which is the e to the negative first minus 1, with n equals 9 terms. So in this problem, the ak is in the term of 1 over k factorial. Recall k factorial means 1 times 2 times 3 times all the way to k minus 1 and k term. Like the 3 factorial means 1 times 2 times 3. 10 factorial means 1 times 2 times 3 times all the way to 9 to 10. So we're going to find the upper bound for the magnitude of the error. The error is the absolute value of the Rn, and with n equals 9, so then the absolute value of the Rn, or the magnitude of the Rn, is less than the An plus 1. Or we can say the absolute value of the Rn is less than the A10 term. And since ak is 1 over k factorial, so the A10 is 1 over 10 factorial. That means the remainder term Rn will be less than 1 over 10 factorial, or is about 2.755 times 10 to the power negative 7, which is called an upper bound. As in the expanded form, so the s, which is negative 1 plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial plus 1 over 6 factorial minus 1 over 7, 1 over 8 factorial minus 1 over 9 factorial plus 1 over 10 factorial minus, and keep going. So for the first 9 term, that is S9. So the S minus S9 equals 1 over 10 factorial minus 1 over 11 factorial plus 1 over 12 factorial minus, and so forth. And the absolute value of this, which is the absolute value of the R9, will be the absolute value of the remaining terms, which less than or equal to which is less than or equal to the absolute value of 1 over 10 factorial, as we interpret this.